Okay, this video and the next one are a very brief introduction to time series data, and this video is about smoothing methods. Time series are data collected at regular time intervals, like every month or every year. The data points are graphed versus time, and it has become conventional to join the points by straight lines. Excel calls this type of chart a line graph. Most people are familiar with these graphs from following the stock market in the news. There are two things to look for in a time series: a long-term trend and a seasonal cycle. This first graph shows a time series with a steadily increasing long-term trend, but nothing else. The second time series not only has a steadily increasing long-term trend, but it also has predictable peaks and valleys that repeat every year. This is evidence of a seasonal cycle. And this last time series really has neither. There is perhaps a long-term downward trend, although that is also far from obvious. This is the kind of time series we'll be looking at in this video, where there are no obvious trends or cycles, so we'll try techniques that smooth out the random-looking bumps in the data. Right, and there are two methods we'll be studying for smoothing: the moving average and exponential smoothing. And here is the data set that we'll practice on. This data set has no clear long-term trend nor a seasonal cycle. The goal of smoothing is to iron out some of these random-looking jumps to the point where we can hopefully see a trend. We'll begin with the moving average, and it is important to note that there is more than one kind of moving average. It all depends on how many time periods you want to use. We'll start with the commonly used 3-period moving average. And here is the first part of the data set over on the left. In order to do a 3-period moving average, we need to average 3 numbers at a time. So we begin with the first 3 numbers, which have an average of 45.67. And notice how this average is placed in the middle of these numbers, or the second row of the data set. Now we move on to the next 3 numbers, and their average is 52. And the next 3 numbers has an average of 45.67, and so on. These averages are called the smoothed values, and we can plot them on top of our original data set like this. The blue dots are the original data, and the red dots are the smoothed values for the 3-period moving average. First, I want to point out that there are no smoothed values for the first and last time period. This is a natural consequence of averaging 3 numbers at a time. And even so, we can already see that many of the peaks and valleys of the original data have been smoothed out. And looking at the red smoothed values, we can see a noticeable, although small, increasing long-term trend, as well as a 4-period cycle. See how there's a peak and a valley that repeats every 4 time periods? Of course, it's a pretty small data set, and we can only see about 3 cycles, so it's hard to say this will continue on and on, but the trend is clear enough in the small data set that we have. Now let's look at the 5-period moving average. This time we'll be averaging 5 numbers at a time. Starting with the first 5, their average is 42.6. And again, this is placed in the middle of these numbers, which is row 3 of the data set. The average of the next 5 numbers is 46. The average of the next 5 numbers is 55, and so on. Again, we'll plot the smoothed values on top of the original data set. Now that we are averaging 5 numbers at a time, there will be no smooth values for the first 2 time periods or the last 2 time periods. And looking at the graph, we get a very clear picture of the slightly increasing long-term trend, but we can no longer see a cycle like in the 3-period moving average. I'll do a bigger comparison of the graphs in a minute. Next, let's see how a 4-period moving average works. In a 4-period moving average, we need to average 4 numbers at a time starting at the beginning. Their average is 48.75. And again, this is placed in the middle of these numbers, which is between the second and third row of the data set. And that's weird, but we'll come back to that. The average of the next 4 numbers is 43.5. The average of the next 4 numbers is 48.25, and so on. And now we have to deal with the fact that our averages lie in between the rows. And we didn't have this problem before because we were using an odd number of time periods. This time we're using 4-period moving average, and it will always be offset like this when we use an even number of time periods. Anyway, the solution is simple. Average these 2 numbers at a time. For example, the average of the first 2 numbers is 46.125, and this is placed in between them, which is nicely lined up with the third row of the data set. The average of the next 2 numbers is 45.85, and that lines up with the fourth row, and so on. This last column is our smooth values. And here is the graph of the smooth values on top of the original data set. Once again, you can see that there are no smooth values for the first 2 and last 2 time periods. And in this graph, we again see the slightly increasing long-term trend. And this graph also seems to hint at a seasonal cycle, but this time it repeats every 3 time periods, not 4. When we do a moving average with more time periods, then the data will be more smooth in the end. So the 5-period moving average would be more smooth than a 3-period moving average. If we smooth a lot, then we take away all of the peaks and valleys in the data, and we'll only be left with a long-term trend. This is fine for getting a good picture of the long-term trend, but this is too much smoothing to see a seasonal cycle if it exists. So smoothing can be a delicate balance. If we smooth too little, then the smooth values will look chaotic, like the original data. If we smooth too much, then the seasonal cycle, if it exists, will be crushed by all the smoothing, and all that we will see is a long-term trend. But if we smooth moderately, then we'll be able to see the seasonal cycle if it exists. To summarize the moving averages that we made for the data set, the 5-period moving average showed the long-term trend clearly, but it smoothed the data so hard that it wiped out any trace of a seasonal cycle, and all that we could see was a long-term trend. The 3-period and 4-period moving averages each show the long-term trend and a cycle as well. However, it remains inconclusive since they show 2 different patterns. This makes me think that we are looking too hard for something that just isn't there. This data set is really small, and the cycles are very subtle, and they only repeat a couple of times before the data set ends. This could very easily be simple random coincidences that we are exaggerating the importance of. So the data has a clear, although small, increasing long-term trend, and it remains unclear whether or not there's a seasonal cycle. It just goes to show that smoothing techniques are as much of an art as a science. Different methods often give seemingly different answers. Good judgment and large sample sizes are always going to be useful. Next, let's move on to the exponential smoothing method, and let's begin with the notation. This method depends on a constant called W, called the smoothing constant. This number must be between 0 and 1, and it may seem backwards, but larger smoothing constant means less smoothing. Next, we use Y to denote the time series data and capital S to denote the smooth value. And each of them has a little number in the corner. To represent the time period. So Y1 would be the data point for time period 1, and S3 would be the smooth value for time period 3. And here is the formula for exponential smoothing. The first smooth value is set equal to the first data point. And then we have this recursive relationship. So S1 is used to find S2, then S2 is used to find S3, and then S3 is used to find S4, and so on. Let's try this out on our practice data set. We'll begin with a smoothing constant of 0.7. Since this is a larger number, we would expect to see not much smoothing. And here is the first part of the data set over on the left. Again, these are the Y values in the formula. Let's start creating the smooth values by making S1 equal to Y1, or 39. Next, to make S2, we need S1 and Y2. If we follow the formula, we get 37.6. Next, to make S3, we need S2 and Y3. And if we follow the formula, we get 53.98. Next, to make S4, we need S3 and Y4. We get a value of 56.79, and this pattern continues all the way until the last data point and the last smooth value. We can plot the smooth values in red on top of the original data in blue. And the first thing I notice is that this is actually very little smoothing. The smooth values look like they're chasing the data points up and down. The peaks aren't quite as high and the valleys aren't quite as deep, but the red smooth values show no signs of a trend or cycle. They look just as random as the original data. We should probably try a smaller smoothing constant. So let's try a smoothing constant of 0.1. We would expect to see a lot of smoothing with a number this low. We begin like before by setting S1 equal to the first data point, or 39. And again, S2 depends on S1 and Y2. We get S2 equal to 38.8. And then S3 depends on S2 and Y3 and is equal to 41.02. And the rest of them follow the same pattern. And when we plot these smooth values in red on top of the original data set in blue, we can see that all of the up and down movement has been smoothed out, and all that is left is the long-term trend showing the slightly increasing trend. So this clearly shows the long-term trend, but this is too much smoothing to detect any seasonal cycle if it exists. And the first example with a smoothing constant of 0.7 had not enough smoothing. I recommend that you try this for yourself with a smoothing constant of around 0.4. That seems to be a good middle ground for this data set. Finally, let's compare and contrast the two methods that we learned today. One of the advantages of moving averages is that it is pretty simple to do and easy to remember. Also, if the data has a natural seasonal cycle, then the matching moving average can lock into its rhythm and remove it. For example, if your data has a natural 4-period cycle to it, then the 4-period moving average will move in unison with that cycle and remove it. The peaks and valleys will consistently cancel each other out, and what will remain is a clear picture of the long-term trend. But there are two disadvantages of the moving average. First, not every time period gets a moving average. First, not every time period gets a smoothed average. The first and last time periods will always be missing smoothed values in a moving average. In our data set, the 5-period and 4-period moving averages had 4 time periods without smoothed values, 2 at the beginning and 2 at the end. Considering that this data set had only 16 numbers in it, 4 missing numbers is a lot. The other disadvantage is that a moving average forgets numbers once it moves past them. For example, consider the third data point. If we are doing a 3-period moving average, then the third data point is a factor in the first 3 averages. But then as we move on, this number is left out and has 0 impact on any of the remaining calculations. Exponential smoothing has none of these problems. There's a smooth value for every time period, and because of the recursive nature of the formula, every past number has a role in the calculation of the next smooth value. Nothing is ever forgotten in exponential smoothing. But one downside of exponential smoothing is that it can't lock into a natural seasonal cycle like a moving average can. Now we have the data sets that you'll need to answer the 3 questions coming up. The first data set has a pretty clear long-term trend and seasonal cycle. And in questions 2 and 3, you'll be practicing smoothing methods on this example data set. Good luck with that, and check out the next video.